Hi, I'm Jiaqi from Singapore Management University. Today I'm going to present a joint work with my supervisor. In this work, we deliver a dynamic analysis infrastructure to instrument untrusted execution flow across user-to-kernel spaces. There are two primary approaches in dynamic malware analysis systems: code instrumentation and hardware-based event trapping. Code instrumentation mixes the analysis code and the target code into one binary, either statically or dynamically. Because of the code mixture, the analyzer and target share the execution flow and also the address space at runtime. Due to the address space sharing, the analyzer has native control towards the target. It's convenient for the analyzer to introspect or modify the target. Where the downside is, there's no transparency or security protection. The target is easy to detect or even attack the analyzer, which are proved by recent works. On the other hand, hardware-based approach relies on hardware events to trap the target to an isolated and more privileged environment, for example, the VMS root mode or ARM secure world. Because the analyzer runs in a higher privileged environment, so this approach guarantees strong security and transparency, and often used for transparent kernel analysis. Where the cons is, the analyzer is not flexible to control or introspect the target due to the isolated environment and semantic gap. So the question we want to answer is, can we combine the advantages of the two approaches without their drawbacks? We propose execution flow instrumentation to interleave instruction strings without mixing the code. To be more specific, the analyzer chooses the site of instruction flow interleaving. When the target executes to the site, the control flow is diverted to the analyzer, where the analyzer runs in a shared address space, which is different from the address space where the target executes in. In this shared address space, it contains mappings not only to the analyzer's memory, but also to the target's memory. So this one-way address space sharing allows the analyzer to have native access to the target, while prevents the target from looking into the analyzer. So we achieve secure, transparent, and native access goals. The EFI approach can be applied on a target spread running in both user and kernel mode. So we also achieve cross-space analysis. We rely on hardware virtualization technology to develop an OASIS infrastructure to support EFI. The big picture is OASIS set up an on-site environment where the target spread is exported from its original guest VM to on-site environment to continue execution, and the host application analyzer is also exported to on-site environment to run on the same CPU core as the target spread. For the analyzer running in on-site environment, OASIS provides three capabilities to it. The first native target access with isolation capability is achieved in this way. The on-site environment has two different paging hierarchies to establish two address spaces for the target spread and for the analyzer spread to execute respectively. The core technique here is to twist in the EPT to redirect the mappings for guest page table pages. We do not copy any of the targets or analyzer's code and data pages to on-site environment. So to be more specific, when the target runs, its on-site root PML4 page table entries are set in the EPT to point to the target's original paging hierarchies used in the guest VM. So in this way, a target address space is established in on-site. When the analyzer runs, except those entries occupied by the target memory, one unused entry in the root PML4 page is redirected in the EPT to point to the analyzer's paging hierarchy in the host. So a shared analyzer and target address base is established for the analyzer to execute, where the analyzer can have native access to the target memory to facilitate the introspection. The switches between these two hierarchies are achieved by using VNFunk instruction. The second capability is on-demand instruction flow interleaving. The analyzer uses software probe to divert the target control flow to the exit gate, which switches the paging hierarchy for the analyzer using VNFunk instruction. After analysis, analyzer jumps to the entry gate, which switches the paging hierarchy for the target. There's no VM transition or CPU mode and privilege changes during these analyzer target switches. With this capability, analyzer can instrument the target's execution flow. Oasis library provides two probes, jump probe and entry probe. The jump probe is multi-byte long, which can be temporarily installed in the target to trace the target execution, where the entry probe can be permanently installed in the target as a breakpoint to monitor its function invocation. The third capability is transparent OS services. The analyzer is initially a host application. When it executes in the on-site environment, we deliver its system calls and exceptions to the host OS to handle. So in this way, we relieve the constraints on the analyzer. It can be developed as a normal C or C++ program, which enjoys the OS services and can invoke fancy existing helper libraries. Because Oasis is a new system, so we developed 3 tools to showcase its capabilities. The first analysis tool is a cross-space control flow tracer. In this tool, the analyzer continuously places a jump probe at the next branch instruction of the target, along with the target execution. So for targets every basic block transport, the execution will be diverted to the analyzer. We apply this tracer tool on 4 different target programs across their user and kernel space execution, and record their total number of system call events, page fault exceptions, and basic block control transfers. We also compare the performance of EFI tracer with mod, which relies on hardware to trap the target into SMM mode on every basic block transport. EFI tracer incurs less times of slowdown than mod on all of the test cases. We also developed 2 EFI tools to working together with a popular kernel fuzzing tool, SysColor. SysColor relies on source code instrumentation to record and validate kernel runtime behaviors. In SysColor, the sysfather generates input to the sys executor. The input is a sequence of system calls with arguments. Then the sys executor invokes those system calls aimed to trigger kernel vulnerability. If a kernel vulnerability is triggered, a crash report is generated. But upon a kernel crash report, it may lack of sufficient information for fine-grained analysis to reason about the crash. Secondly, it is not able to handle proprietary drivers without source code instrumentation or malicious modules equipped with anti-instrument techniques. So we developed 2 EFI tools to complement it. In both of the case studies, the sys executor is exported to on-site environment to undergo EFI analysis. In this dynamic post-mortem analysis case study, SysColor reports a crash caused by a page fault in the kernel function when it accesses an array element. We develop an EFI analyzer to collect runtime data in order to reason about the page fault. So this is done in 2 phases. In the pre-processing phase, we use backward slicing upon the failed instruction to determine the size to install EFI jump probe. Then at runtime, the analyzer installs an in3 probe at the target interesting function to monitor its invocation. When the function is invoked, then the analyzer installs jump probe at the slice instruction. The jump probe at each slice instruction would pass the control to the analyzer so that it can fetch the necessary kernel objects using native kernel introspection. With the runtime collected data, we found out that the code incrementing the array index is never executed, which leads to an out-of-bound memory reference. In this exploration of untrusted driver case study, we developed an EFI tool to work together with Syscaller to uncover the hidden behaviors of an uninstrumented kernel space driver. So we customized a rootkit from GitHub by hiding its malicious behaviors in a hidden path, and also adjust it to equip an anti-instrument technique to against the ftrace logging. Then at runtime, Syscaller generates fuzzy input to trigger the hidden path, while the EFI analyzer records the malicious driver's behaviors, including the control flow transfers within the driver itself and also its invocation to kernel functions. We implement an Oasis prototype on an x64 platform running Linux kernel 3.13. We also run some micro and macro benchmark testing to evaluate the performance, and also some benchmark testing to evaluate the transparency. We compare the round-trip transition time between the analyzer and the target with Spider, which traps the target into hypervisor, and Mode, which traps the target into SMM mode. The EFI jump probe is 3 times faster than Spider and 32 times faster than Mode. To evaluate the Oasis impact on the guest VM hosting the target program, we run LM bench in the guest VM and continuously capture its spread to on-site environment for EFI trace. The highest overhead is on the file system latency, where the EFI trace incurs 10% overhead on it. We also evaluate the transparency of Oasis by applying EFI tracer on several benchmarks to see whether those benchmarks can detect the system environment or software state change. The first is an anti-debugging benchmark named Pangu, which is equipped with several popular anti-debugging techniques. The second is a self-checksum program, which calculates a hash digest of its executable and read-only data memory, and an anti-instrument benchmark tool, which detects address-based change, and so on. Finally, we apply EFI tracer on a UPX-packed share command program uname. Among all experiments, only one technique in Pangu, which uses RDTSC to measure its execution time for loop, detects the tracing analysis. Due to the prolonged execution time, all of the other transparency testing are passed. As a summary, we propose EFI, which combines the benefits of 2 mainstream analysis approaches. We design and implement Oasis to support EFI. Analyzer running in on-site environment is easy to instrument and also introspect the target threat with security and transparency protection. Oasis system has the potential to support a wide range of applications, such as to deal with malware equipped with anti-analysis techniques, like forensics at attacker sites, and complicated kernel analysis. Oasis can also be exported to ARM platform, but in that case, trapping to hypervisor might be unavoidable because the lack of equivalent VM func instruction in ARM. We made the source code available at GitHub. Thank you for coming. Any questions?